So let's try another one here. Okay, this is, let's state the non-principal value. So we're going to say that sine x is not equal to 0 and cos x is not equal to -1. Okay, so those are my non-permissible values. When I look at this, I can, one of the strategies I can use, and again, this is another strategy, so you should be making note of these different strategies. One strategy is to make the denominators of both sides look the same. And when we do that, often the numerators then will follow, because it's hard to kind of work with both numerator and denominator. So what we can do is if we make the denominators the same, then we just have to worry about the numerators. So what I'm going to do here is I'm going to multiply the bottom by 1 plus cos x and the top by 1 plus cos x. Okay, because if I multiply top and bottom of a fraction by the same expression, it doesn't change the expression. To get a common denominator over here, I'm going to multiply by sine x and the bottom here by sine x. Okay, so what I end up with then, I get sine squared x on the top. I have sine x times 1 plus cos x on the bottom. And on this side, it's going to equal to, when I FOIL that all out, I get 1 minus cos squared x. And I end up with the common denominator sine x, 1 plus cos x. So once I have the denominators equivalent, I don't need to touch those anymore. Those are now looking exactly the same algebraically. So all I have to do is worry about making the numerators look the same. Well, the numerators in this case, this is a Pythagorean identity. 1 minus cos really is sine squared. So 1 minus cos squared is sine squared. And so I end up with sine x, 1 plus cos x in the denominator. Left side looks like the right side. Check. And again, this is only one way to do it. Okay, there's many different ways to do it. I could have not bothered doing anything to the left-hand side, and I could have done one more step here. And notice that sine squared and sine would cancel out. I end up with 1 plus cos x, and that's looking like the original here. So I could have avoided doing anything on the left-hand side and just simplified like that. Okay, so those are just options that we have. But again, once we make the left-hand side look like the right-hand side, my identity is proven. Okay, so these are some easier ones. Again, we want to start developing some strategies and ways to kind of deal with these. So some of the keys then is you want to write proof statements underneath each other. So each step, you can see clearly what the algebraic step was. You can work on either side. Okay, you can work on left side only, right side only, or on both sides. One of the keys is do not solve these equations. These are not equations to solve. They're identities. They're different. Okay, because these are true for all values of x, as opposed to an equation which we're solving for unique x's. So one way to describe it is an identity traces on top of each other. Okay, they are algebraically the same. Oops, what happened to my identity there? Okay, it's algebraically the same. Okay, it just stays the same. Whereas an equation, where you would have a graph, and then you would have another graph where they intersect and they have unique, discrete solutions. They don't overlap. Okay, so identity overlaps, equations have intersections. So these aren't equations as well, so we can't add and subtract from both sides. Okay, so we can't say, we can't say plus x on this side and plus x on this side. Okay, we can't treat it like that because we're trying to actually do the logic behind it is you're trying to prove that they're equal. So we can't use these properties of equality to prove that something are equal. Okay, that's not logically a very good way to prove something. The fewer steps, the better. Okay, so, but if you go and do a big long proof, if it's valid, it's perfectly fine. There's nothing wrong with it, but you should try to be more efficient. One of the things I don't want to see is you going into loops. Okay, so you transform something on one side, and on that same side you transfer it back to a statement that you had before. Okay, so we don't want to get into those loops. And last thing here is that these
transformations are really important once you get into calculus, because we use these all the time in calculus to make things change expressions so that they're much easier to work